Aerospace environments generate massive thermal loads, while semiconductor packaging relies on tolerances measured in micrometers. Both extremes demand materials that maintain structural integrity under intense heat and pressure. Traditional ceramics can survive these conditions, but their manufacturing process is limited by geometry. Because they rely on powder metallurgy and high-temperature sintering, they cannot be applied as thin, conformal coatings over intricate or nonlinear surfaces. Polymer-derived ceramics, or PDCs, offer a different path. These are pre-ceramic polymers designed to bypass the traditional sintering process. Instead of pressing and baking powders, engineers apply these polymers as a liquid film. They can be dipped, spun, or sprayed directly onto complex parts to create a uniform, conformal layer. Once applied, heat triggers a phase transition. The liquid polymer solidifies, converting the molecular network into a rigid, silicon-based ceramic. However, this transition induces massive volumetric shrinkage. Success with PDCs requires mastering the interface and defect engineering needed to manage the structural collapse. We examine precursor chemistry to understand shrinkage. This polysilicene network highlights the silicon-nitrogen and silicon-oxygen backbones. Low-temperature cross-linking forces chains to branch, locking into a solid matrix. Pyrolysis drives off organic molecules, causing mass loss. The remaining lattice compresses, pulling against the substrate, forming microcracks. As the organic components vanish, the remaining silicon-based network reorganizes. It settles into an amorphous ceramic state, typically forming silicon carbon nitride or silicon oxycarbon nitride. During this reorganization, secondary microstructural features emerge. The material develops distinct nanoscale domains and a tunable free carbon phase. This creates a direct engineering conflict. Heat required to build the ceramic's thermal stability simultaneously threatens its mechanical adhesion to the surface. In harsh environments, this microcracking leads to failure. Marine corrosion targets these microscopic defects to accelerate structural degradation and deep pitting on metal surfaces. Unmodified PDC layers often fail in these conditions. Shrinkage-induced microcracks create direct pathways for corrosive ions to reach the underlying metal. The solution lies in chemical modification. By reacting the polysilicene precursor with MTES, engineers can increase the cross-link density before the pyrolysis phase begins. Electrochemical impedance spectroscopy data shows the standard curve dropping, while the MTES modified line maintains a stable, high-impedance plateau. This indicates a dense, crack-free barrier, suppressing corrosion current density by physically blocking chloride ions from penetrating the substrate. Aerospace data confirms this mechanical integrity. Applying a silicon carbon nitride film over anodized aluminum creates a multi-layer barrier that resists high-stress friction. The resulting tribological metrics show significant reductions in wear rates, coupled with increases in both localized hardness and the surface modulus. By tuning the precursor chemistry, engineers turn a porous shrinkage layer into an impermeable, load-bearing protective coating. PDCs also serve functional roles in managing electromagnetic cross-forms. Radar-absorbing materials, or RAM, are designed to intercept incoming electromagnetic energy and dissipate it as heat, rather than deflecting it. The mathematical metric for this dissipation is the dielectric loss tangent. The imaginary permittivity, or loss factor, determines how much energy the material can absorb. Baseline silicon oxycarbon nitride films offer limited dielectric loss. To increase absorption, engineers integrate titanium dioxide fillers directly into the pre-ceramic polymer. This graph shows the modified loss tangent curve peaking sharply within specific high-frequency radar bands. The titanium dioxide fillers create interface polarization within the amorphous carbon network. This mechanism converts incoming electromagnetic wave energy into thermal dissipation. Manipulating the free carbon phase and filler additives allow PDCs to absorb electromagnetic energy, a capability distinct from traditional structural ceramics. This level of interface control is equally critical at the micrometer scale of advanced semiconductor packaging. In these environments, the primary reliability bottleneck is maintaining adhesion on copper redistribution layers during intense dermal cycling. Traditional polyimide interfaces often struggle under these conditions. Polysilicene-derived coatings offer superior thermal stability, but they require a flawless bond to the copper surface. To achieve this bond, engineers use oxygen plasma treatment. The plasma alters the surface chemistry of the copper, allowing the liquid PDC to spread completely across the surface. This modified surface energy, combined with exact curing parameters, significantly increases the final peel strength of the interface. Whether securing a copper trace on a microchip or defending a steel hull, interface control is the primary factor determining PDC reliability. Across these case studies, the advantage of PDCs lies in using liquid precursors to engineer multifunctional boundaries rather than bulk components. The first major frontier in scaling PDC manufacturing is eliminating slow thermal cross-linking. Engineers are now using UV curing for filled polysilicone coatings, which solidifies the polymer instantly without the need for external heat. UV curing increases industrial throughput while maintaining the chemical resistance of the final ceramic layer. The second frontier is additive manufacturing. Facilities are now 3D printing complex silicon oxycarbide and silicon carbon nitride parts directly from liquid pre-ceramic polymers. Even with 3D printing, the shrinkage paradox remains the primary obstacle to achieving exact dimensional accuracy. PDCs allow for the complex shaping of polymers to result in the environmental stability of ceramics. Their future application depends entirely on how effectively engineers design interfaces to manage the defects inherent in their transition.